Oh my goodness, we are almost finished with the structure of amino acids. Can you believe it? We have now covered 15 of the 20. We have 5 left, and the ones that we're going to focus on this video will be the benzene-containing amino acids. So we have 2 of these truly benzene-containing amino acids that are out there. And we're going to look at the structures of these two. They're very similar in structure. There is one modification with them, and that is it. So let's start off by starting with the foundation of the amino acid, and here it is, NH3 plus HCOO minus. Please keep in mind that the COO minus is actually the same thing as a C double bond OO minus, which is really the same thing as COOH and C double bond OOH, depending on the pH that you put it in. That was a mouthful, right? Okay, so let's take a look at our first benzene-containing group. So we have this middle carbon with a CH2 group there, and then off of this middle carbon we see our benzene ring. So there is our first benzene-containing amino acid. And this benzene-containing amino acid is going to be called phenyl, P-H-E-N-Y-L. Now that's not all. But this is a very common name that we've always used in organic, right? We said phenyl represents the benzene ring. If we get something directly attached to the benzene ring, that is called the phenyl group. Well, the other one that we had was called the benzyl group. So why didn't we use benzyl here? Because benzyl was actually a ring with a middle carbon onto the main chain, and it looks like that's what we have here. We've got this extenuation of the CH2 group, and then the benzene ring follows. So we said before that if the main chain's directly connected to this, that's called phenyl. But if the main chain is connected to that, then that's called benzyl. So why isn't this benzyl? Well, the reason is because we are starting with a group name for the amino acid. And we understand that if this was CH3 here, well, this amino acid, if we forget about the benzene ring down here below, the amino acid that I have drawn with just a CH3 group there is called alanine, right? Okay, well, if I can delete one of those hydrogens and substitute it for a benzene ring, then we can call this phenylalanine, and that is the name for that structure. So if you know the structure for alanine, well, that's good. You just really have to delete a hydrogen, put a benzene ring on now instead, and this will give you phenylalanine. So that's the only thing that we have done and modified as far as the alanine structure is concerned. So phenylalanine. Okay, so what's the 3-letter abbreviation? Well, this is kind of easy. PHE. They've always kind of fell in hand. We can at least try to figure the majority of them out with the first 3 letters. Not every time, but most of the time we can. The problem, though, is that the 1-letter abbreviation, we would probably want to put down P, and P is wrong. P actually goes with another amino acid that we haven't focused on yet. We haven't talked about that one yet. So P is out of the ballpark. We can't use that. So when we say phenylalanine, it's kind of like phone, right? We almost say the letter F. So phenylalanine. So because of that, they chose F as the 1-letter abbreviation for phenylalanine. So just like the phenyl that you might cook with in your kitchen, maybe some of you know what phenyl is. I hope you do. So I hope we've got some cooks in the class. Good cooks make good chemists. Keep that in mind, please. So phenylalanine, PHE, and F. Okay, now once we have the phenylalanine structure, we can actually go ahead and go straight to the next amino acid that's the benzene-containing amino acid. So it starts off with phenylalanine, and the only difference here is that we've got something else on the ring, and this is a OH group. So if we can draw phenylalanine, then we can draw our second benzene-containing amino acid. And this is called tyrosine. T-Y-R-O-S-I-N-E. So tyrosine. Tyrosine's 3-letter abbreviation, well, tyrosine, like you would expect, would be T-Y-R-O-S-I-N-E. And TYR, tyrosine, well, T is not going to be used for the one-letter abbreviation for tyrosine. What will be used, however, is a Y. So that kind of separates it from some of the other amino acids that we have seen so far. I mean, you take a look at the names of some of these amino acids, and there's very few of them that have a Y in the name. Phenylalanine has a Y in the name, but the focus is put on the F for phenyl. Here, we finally get tyrosine, and we can kind of see Y as a priority in the actual name of it. So that's why they use Y as a one-letter abbreviation. At least that's the way you can think about it. So these are the two amino acids that are the benzene-containing amino acids. So phenylalanine and tyrosine. Now, the good news here is that they contain benzene rings. So benzene is aromatic. And aromatic means UV-vis. Okay, so I'm going to put big stars beside of these two because part of our job in this program is to get very comfortable with instrumentation and figure out when and why and how to use the instrumentation that we have in our lab and facilities, right? So all of these amino acids that we have talked about up to this point, they really do not show that much UV-vis absorbance reads. And the reason is because UV-vis absorbance typically plays off of absorbance of light, and with organic molecules that have colorless solutions, well, these solutions, the only way they can absorb UV light is if they have some kind of aromatic ring or delocalized electrons or some free pairs of electrons. And phenylalanine and tyrosine are very good amino acids to measure in a UV-vis spectrometer. And we measure them in a UV-vis spectrometer alone, without anything else with them. And they show up very nice banding, very nice absorbances. We can make solutions of them. We can see the spectra. We can print off the spectra and do calculations with them. However, if they are in a protein, and they will be, well, we can play off of these protein UV-vis absorbances as well. So when we get to the point where we talk about analysis of proteins, we can analyze them with a UV-vis spectrometer. The reason that we can analyze them with a UV-vis spectrometer is because of these two. It's because of the phenylalanine and the tyrosine. They have very good aromatic rings, and these rings absorb at UV range. Whether they're alone as an amino acid or whether they're part of a protein, it does not matter. So those were the take-home things that you hopefully learned in our first instrumentation class when it concerned UV-vis spectrometry. So you looked at UV-vis, we talked about why things absorb the way that they did, and these are two molecules that will absorb in UV region, so 200 to 400 nanometers. Don't ever forget that range, that's very important, right? So UV-vis, so in the UV portion, 200 to 400 nanometers, we can see phenylalanine and tyrosine being absorbed. Now, I have to be honest, this is not the only two amino acids that will absorb in UV range. There is a third one that does absorb very well, and that's our next set of amino acids, and that one is going to be called tryptophan. So phenylalanine, tyrosine, and tryptophan are all going to provide you some UV absorbance reads with these proteins and amino acid solutions. So we're going to look at tryptophan in the next video because its structure is a little different. It does have a benzene ring, but we're going to call it a heterocyclic amino acid because there's other things just than a benzene ring. So we'll take a look at it in the next video. But these are two amino acids that give you UV-vis. Remember their structures, they're very important, probably two of the most important ones in the bunch, just because this is how we do some analytical chemistry and measurements with amino acids and proteins in general. So in the next video, we'll finish up the amino acid structures. We'll talk about our last three, and our last three focus on heterocyclic rings. So one more, and you are finished. It's time to go for a drink.